Sounds good.
It's yours.
All right, this presentation is called Sultaines, a more sustainable alternative to traditional amphoterics. So for our outline here, what we're going to be covering during the course of this presentation are, first off, basically an overview of Sultaine chemistry. What are Sultaines? How are they manufactured? How they can improve sustainability, and some additional product features that are associated with Sultaines uniquely compared to other product classes. We'll go through some commercial examples of Sultaines, including traditional coconut-based products, some newer feedstocks that are available for use to elicit some interesting new effects, and what the performance attributes of both the traditional and newer feedstocks look like. We'll also talk about some continued development that's occurring in this chemistry area that will continue to improve sustainability throughout supply chain. So first, we're going to start by talking about betaines versus sultaines. Now, everybody is fairly familiar with traditional betaine chemistry. Here we have our imidapropyl type betaine structure, starting from the left with our fatty alkyl group, going through the amide, and then we have a quaternary nitrogen that's a permanent quat, and then the carboxylate group that terminates. Sultaines are structurally quite similar in that they start with the same amidoamine type structure to start. Instead of placing on, however, the carboxylate, we're substituting the hydroxypropyl sulfonate functional group. So whereas a traditional betaine, it will terminate here with the anion being a carboxylic acid type, the Sultaine terminates with this sulfonate structure that's connected through the hydroxypropyl linkage to the quaternary nitrogen. So in terms of how these chemicals are manufactured, betaines are two-step synthesis, where we start first with the synthesis of the amidoamine. This can start from a variety of oleochemical feedstocks. Then in the next step, we perform the carboxylation via either monochloroacetic acid or sodium monochloroacetate. These are traditionally petrochemically derived carboxylate intermediates. And that produces our betaine with sodium chloride as a byproduct of the reaction. For the Sultaine chemistry, the first step is identical in terms of the synthesis of the amidoamine, again using the same feedstocks here. The main difference again is in the second step. Instead of doing the carboxylation, we're doing the hydroxypropyl sulfonation via intermediates often referred to as CHIPS. This CHIPS intermediate can be petrochemical or biorenewable. The majority of manufacturers using the intermediate are using the petrochemical right now, but starting to see some movement towards the biorenewable feedstock, and we certainly are trying to incorporate that ourselves. This reaction product gives the Sultaine with the same sodium chloride byproduct as we got via the monochloroacetic acid. So when we look at feedstocks for these chemistries, both the betaines and sultaines are made from a variety of sources, can be identical sources. Those include the whole triglyceride oils, These would be things like coconut oil or palm kernel oil. Um, Other triglyceride oils have been used and can be used. We can use fractionated oils, so things like mid-chain triglycerides, or um, sometimes also known as caprylic capric triglyceride, could be used to produce this chemistry. It could be produced from fatty acids, either whole fatty acids like coconut, retaining the entire distribution of fatty acids from C8 through C18, or we can use distilled fatty acids. In some cases, we use portions like a C8 or C810, or the mid chains for highest foaming performance typically, and then sometimes longer chain lengths for uh, greater viscosity building or other benefits. Just like the fatty acids, can also use methyl esters to produce these products. The methyl esters, again, can be whole or distilled. Um, Typically, when we're using methyl esters, we are using distilled products. And finally, we can use fatty tertiary amines. And these are end products in the oleochemical chain that we'll show you how we get to in just a moment here. But the main thing to note is that by using primarily our whole oil, the feedstock supply chain transparency is better managed. We're bringing in complete triglyceride oils. We're confident of the identity of that oil, making sure that it's exactly what we think that it is. So as we go further down the value chain, we start to increase chances of commingling feedstocks because there are a number of different oils that can be useful in contributing certain fractions to this value chain. So here's what that looks like. Basically, starting from the top with triglyceride oil. Again, this is something that we could use as a raw material and produce products from. But typically, these oils will undergo some sort of hydrolysis and will, during that step, produce glycerin as a byproduct, which is fairly high value in itself. Can be converted for use as a humectant in a variety of personal care applications. Fatty acids that are produced there then can be used directly as a feedstock, or they can be distilled and fractionated. Another step that can take place once we produce the fatty acids is to produce the fatty acid methyl esters. And again, those can be distilled and fractionated or used as the whole methyl ester. Methanol is used as an input there, and the excess is typically removed at the end of the production. Next step, we can hydrogenate further from the methyl ester to produce a fatty alcohol. And those fatty alcohols, again, are typically distilled and fractionated. Things like cetyl alcohol and other fatty alcohols are produced in this way. And then in the final step, we can react the fatty alcohol with dimethylamine, which is itself a reaction product of ammonia and methanol, and produce the fatty dimethylamine, which is tertiary amine. And so you can see that, again, as we work down the value chain, you have more and more opportunities to commingle feedstocks to produce the optimum mixtures of alkyl groups. One common thing that's done in the industry is, for example, at the triglyceride step, we'll maybe start with coconut or palm kernel. And then as we work our way through Things like C12 or C1214 methyl esters are typically some combination of those feedstocks. Same goes for the fatty alcohols, fatty dimethylamines. Like I said, it becomes fairly opaque in terms of the feedstocks and ability to trace the exact identity of the oils that are going in by the time those processes take place. And the oleochemicals are typically, produced by large manufacturers in their own right, and they do these for a wide variety of industries, not just personal care. So, in terms of improving sustainability of surfactants, we know that manufacturers of chemical intermediates are typically very slow to change. Um, the intermediates are going into a lot of different end-use products, and in a lot of cases, those end-use products are not as demanding of improved sustainability as we are in the personal care realm. And making traditional amphoterics 100% bio-based is technically feasible. Um, Things like the fatty dimethylamines could use bio-based methanol, that's produced from, you know, fermenting a variety of cellulosic products. Um, Even the MCA or SMCA feedstock that we talked about for the betaines could be produced from a bio-based acetic acid, again from fermentation. But those intermediates are to date not uh, bio-based right now. So we're kind of waiting in the wings for folks to do that. Well, what has happened recently is that a commodity chemical used to produce sultanes has gone from its traditional petrochemical to being available now as something from a sustainable source. Sustainable source of that material is glycerin that's produced as again as that first byproduct in the hydrolysis of triglyceride oils to produce fatty acids and fatty acid methyl esters, fatty alcohols, and fatty amines. The Sultaine chemistry, based on the structures we looked at earlier, would typically contain one more black carbon from the petrochemical intermediates. By, but by turning that intermediate to a bio-based source, we have a very significant impact on the final product sustainability. So a traditional cocometapropyl betaine might be about 65% bio-based content. Cocometapropyl hydroxysultaine from the petrochemical intermediate would be reduced somewhat to about 60% bio-based. However, when we use the bio-based intermediate instead of the petrochemical intermediate, we have now improved the bio-based content to around 80%, just slightly shy of that. So you can see by substituting this one intermediate, we've been able to make a fairly strong headway in improving the sustainability of these types of surfactants. So you may wonder, well, how do betaines and sultanes then compare to each other? Familiar with betaines, but maybe not quite as much as sultanes. And so they have a lot of common features. So they are both useful for providing foam stabilization, improving foam density by decreasing bubble size and compactness of the foam, improving the viscosity response of anionic surfactants by increasing the overall um, salt response of these molecules. They lower the CMC of formulation, or the critical micelle content, when combined with anionics, and that's useful for improving detergency, improving wetting, and many other properties. But importantly, especially in the personal care arena, by lowering CMC, we're also able to reduce the irritation of primary surfactants. And that's one of the key uses for this type of chemistry and formulation. We can improve solubility of marginally soluble additives. Betaines and sultanes tend to be better emulsifiers than traditional primary surfactants, things like SLS or SLES. Um, Betaines and sultanes improve detergency, they improve wetting, and have just an overall benefit of making those anionic surfactants work better in formulations. There are some differences in terms of performance of these products, and so sultanes offer some additional unique benefits, and that includes things like higher solids. So a typical sultaine can be produced easily at 50% solids rather than typical betaine, which is produced at 35% solids. This does not require any special additives, processing aids, or changes in manufacturing equipment to do this. And so it's very easy to obtain a more sustainable product, even just from the footprint of using less water and shipping around less water in the finished surfactant. The sultanes offer the same or better viscosity response by active. In many cases, you will see very good parity. Um, this is, of course, to a certain extent formulation dependent, but we will see some model formulations and how these look in comparison in just a moment. Sultanes are supplied preservative-free without any caustic pH. So a typical betaine would contain a preservative. Used to be, of course, formaldehyde donors. We don't do that anymore, but in the effort to move away from formaldehyde donors, many betaines started becoming preserved with Cathon and or that type of isothiazolinone preservative chemistry, which we know now has some sensitization issues for human skin, can cause allergic reactions. So the industry, again, in personal care is moving away from the isothiazolinone chemistry, and we're working towards either alternate or preservative-free options. For betaines, going preservative-free either requires having clean process and having an end product that must be kept in sealed drums and could be susceptible to growth with improper handling, or betaines can be have their pH increased to very high pH to ensure um, the antimicrobial aspect. Sultanes do not require any of that higher pH to do that because of the higher solids, a little bit higher salt as well. So we're reducing water activity, increasing salt concentration, and the finished product is inherently better self-preserving. Sultanes have a lower inherent irritation potential when compared to betaines. We'll be looking at a bit of that data in just a moment here to substantiate that. Another key aspect of sultanes is that they have improved compatibility in hard water and certainly can help fatty acids and fatty acid soaps to not precipitate from hard water. The carboxylate group of the betaine is more prone to precipitation when combined with calcium, and we see much less of that with the sulfonate anionic portion of the sultaine chemistry. Sultanes also help disperse those lime soaps, as they're called, or the fatty acid calcium soaps. And so in formulations where formulators are working with a fatty acid or many sulfate-free surfactants like isocyanates contain some free fatty acid. Those will precipitate in combination with calcium in hard water and can cause undesirable film formation either on the hair or skin or especially in wash basins, tubs, and sinks. The EWG has assigned a lower score to typical cocamidopropyl hydroxysultaine uh, compared to cocamidopropyl betaine. Sultaines gets a 1 EWG score, whereas betaine can score up to a 5 depending on use. Um, it's not exactly clear what the EWG requirements are to obtain the lowest score for the betaine, which is 2. Um, but the Sultaine is pretty much without restriction a lower score. Finally, Sultaines do not contain any dichloroacetic acid byproduct, which improves the California Prop 65 compliance. Just a quick word on dichloroacetic acid. Um, this is something that's listed on the California Prop 65, has been for many years, first listed in the original list in 1996. It's had some additional flags added in 2009 and has been undergoing some additional potential action as recent as 2013. There is no safe harbor limit established for dichloroacetic acid. So by the letter of the law for this California Prop 65, um, the producer of a product, end use product, would either have to establish that there is no dichloroacetic acid detectable in the product, or would have to have some rationale for not listing it as a potential carcinogen. So, due to a large number of consumer products which contain betaines, it could be that this type of chemistry comes under higher scrutiny, and products could be in the future subject to the sorts of Prop 65 warnings that you may see on some other items. Okay. So now that we've gone over the Sultaine chemistry, we're going to talk here now about Sultaines and applications and how they're useful ingredients and how they can readily replace traditional betaines. First, wanted to look at an overview of what's commercially available in the market right now. Um, there has been for quite some time available cocamidopropyl hydroxysultaine. These can be obtained from coconut oil or coconut fatty acid are the two most common feedstocks. The main difference between those two grades would be the presence or not presence of glycerin as the end product when we're working with the triglyceride oil to start with. About 3% glycerin is produced as a byproduct and remains in the Sultaine as supplied. When we start to produce from the fatty acids, we do now have the option, of course, to look at fractionated fatty acids, and those will potentially give higher viscosity building in addition to not having the glycerin byproduct. Also available is loramidopropyl hydroxysultaine. This is typically produced from fractionated palm kernel or coconut methyl esters. It's pretty rare that you can find the methyl esters that are identity preserved to the coconuts. And so typically we're looking at something that contains some portion of palm kernel oil and can be, of course, produced with mass balance grade palm kernel oil if necessary. These again would be glycerin free as we again move down that oleochemical value chain, and we have the potential now because we've reduced the C8, C10 content to have very efficient viscosity building, and because we don't have any unsaturated fatty acids, we typically have very low color and odor associated with these as well. Another commercially available product is the lauryl hydroxysultaine. This comes from the tertiary amine. Again, typically fractionated palm kernel derivatization gets you to here. The lauryl hydroxysultaine from the tertiary amine does not have the amido-functional group, and that allows it to have the best hydrolytic stability, which will mean that it'll have better stability in very low and very high pH systems. Also, because it doesn't have the midopropyl type linkage, it has a higher biobase content relative to the imidopropyl type products. Unfortunately, these sultanes from the tertiary amines, is like their betaine counterparts, while they have shorter names, don't offer the same viscosity building potential as the imidopropyl types, and that's why those are preferred typically. Some newer additions into the marketplace. We have Babasa midopropyl hydroxysultaine, produced from babasu oil, which is a Brazilian oil source, which provides similar performance to coconut, but gets us away from the coconut or palm kernel confusion. Then finally, very new to the marketplace, has been introduced hemp seed imidopropyl hydroxysultaine. That's a proposed inky name for that product. This is derived from hemp seed oil. The hemp seed oil is free from any THC or CBD, so it is globally compliant from the standpoint of being free from those potential contaminants. The hemp seed oil is primarily a very long chain triglycerides, C18, and so the primary benefits of the hemp seed derivatives is not as much in the foam stabilization, foam boosting, but more in the viscosity boosting. And again, we'll see some data supporting that in just a moment. And again, because we're producing this from the full oil, it does contain glycerin as a byproduct. Due to the longer chain length, it also has a higher natural content relative to the coconut or palm kernel derivatives. Looking at foam and other surfactant performance of the sultanes relative to their betaine counterparts, here we're looking at side-by-side coconut oil betaine and sultaine, coconut fatty acid derived betaine and sultaine, and coconut or palm kernel derived methyl ester betaine and sultaine together. And you can see for most aspects, the performance is parity. Any small differences that we see in the numbers here, we wouldn't expect to be consumer perceivable in a formulated product. Here we can see how the foam compares in a formulated system between these different variants. From the betaine, sultanes from similar or alternate sources. In all these formulations, we reduced the amount of the sultaine due to its higher activity, proportionate to the solids content. So for the 35% solid betaine, we're using 5%. For the 50% solid sultanes, we're using 3.7%. See, again, that's very little difference of note between these formulated products in terms of their foam performance when switching from betaine to sultaine. And this is DI water foam performance. Again, where we're really going to see a boost in the efficacy of these sultanes is in hard water, especially when they're in the presence of some hard water soaps. Here, looking at viscosity performance of the oil-derived betaine versus the variety of sultanes that we can compare to. We can see that when we're comparing the 5% betaine from the oil to the 3%, which is equivalent solids, sultaine from the same oil, we get nearly identical performance in terms of viscosity building. When we move away from the oil-based products to the fatty acid or fatty acid methyl ester products, you can see we can adjust and improve viscosity response beyond what we can get from the whole oil. Looking at the alternate feedstock, the non-traditional babassu oil, again, we see very similar foam performance when comparing the coconut oil to the babassu oil in both deionized and tap water. And again, you can see that's a little bit better performance in the tap water from the babassu oil sultaine, which is what we see also in terms of viscosity response with the babassu derivative. We see a little bit better performance there. This is partially due to the subtle differences between the coconut oil and the babassu oil in terms of their fatty acid distribution. So very similar performance, moving away from the coconut or palm kernel type oil stock to the Brazilian babassu here. In this case, we're looking at the hemp seed sultaine and how it's affecting viscosity performance. Because of the longer chain length associated with the hemp seed sultaine, we do know that it has very strong viscosity response that's predicted. What we do see here, and want to point out in these graphs, is that it's well accepted that things like Cocomet MIPA or Cocomet MEA are viscosity boosters, but they typically don't improve viscosity a tremendous amount over the baseline. What they do is they shift the amount of salt that's required to achieve the higher viscosity quite substantially. And so what we're seeing with the hemp seed sultaine is we are seeing a very significant increase in the total amount of the viscosity potential that's we can achieve with the system. And by combining, for example, a traditional betaine or sultaine with some of the hemp seed sultaine and a small amount of alkanolamide, you would be able to then formulate a product with very high viscosity potential, relatively low salt usage, and then get away from some of the petrochemically derived PEG type thickeners, which are used currently in the industry to do this same effect of increasing the total or highest point of the salt curve. In terms of the toxicological properties of sultanes and how they compare to betaines, we looked at eye irritation under the MatTek Epiocular in vitro eye irritation protocol, a 4% solids, which is fairly typical use level for a cocometapropyl hydroxysultaine, scores in the non-irritating or minimal irritating range for that test. This is what the bands for that testing look like. The time to get the 50% inhibition is measured. Longer time means less irritating. Also done HET cam irritation. This is another in vitro scoring protocol. At 4% solids, we get an irritation score of 12, which puts it in the moderate tier. That would make it equivalent to a typical or leading brand baby shampoo. Um, for comparison, the cocometapropyl betaine would have an equivalent solids an irritation score of about 18. Um, Maximum score for that is 30. For skin irritation, both the ECHA database and the CIR indicate no potential for skin irritation. Same thing for skin sensitization. Product is sultanes in general and cocometapropyl hydroxysultaine in particular are readily biodegradable according to the OECD 301D protocol. And under the EU Cosmetics Directive, there are no Annex 3 restrictions for the use of sultanes. In terms of future development and where we see the sultanes evolving and being even more useful into the future. First, we can perform the same hydroxypropyl sulfonation on imidazoline intermediates. And so the product class known as amphoacetates now could potentially be replaced by these, again, for improved sustainability from the bio-based standpoint, but also would have even milder irritation profiles compared to the sultanes, and the fully amphoteric structure of these products offer a variety of added benefits over a broad pH range. We continue to investigate performance benefits of alternate oil feedstocks. That includes underutilized oil seeds, things that may be cropped for other reasons, and the seeds and their associated oils are not typically a value product for those crops. Oils produced via algae or other biosynthetic roots. And we can, of course, continue to scour the supply chain for additional sustainability improvements. And this includes all the components and intermediates throughout. That would be, like I had mentioned before, if there were ever 100% bio-based tertiary amines, we would start evaluating those. Certainly looking at better feedstock transparency, looking towards tertiary amines that are potentially palm-free. And again, as I mentioned towards the beginning of this, we do see perhaps that bio-based monochloroacetic acid or sodium monochloroacetate may be on the horizon, but unfortunately not commercially available yet. So we believe that this Sultaine route is the most sustainable available route right now to producing the benefits and properties that are associated with these valuable secondary surfactants. That's a wrap.